This video, we're going to talk about 6.2, which is solutions about ordinary points. These are specifically series solutions. So let's go ahead and get started here with number 3 from the textbook. And in number 3 and number 5, we're going to find the series solution, and then we're also going to go back to our methods of solving homogeneous linear differential equations with constant coefficients from section 4.3 and prove that our series solutions that we found are actually power series representations of those solutions that we expected from 4.3. So these might be problems that we already did in 4.3, but let's go ahead and solve them this way. I'm going to write a power series as n equals 0 to infinity. C sub n is my real coefficient that goes with the term x to the n. So starting with a constant and working up to the nth degree of the polynomial here, but we're taking this function and using a Taylor series or Maclaurin series, I forget which is centered at 0, I think Maclaurin. And so this is a Maclaurin series centered at x equals 0. So y prime is going to be, and we just take derivatives according to the power rule here. So this is going to be n c sub n x to the n minus 1. Now we can ignore any terms where we're adding 0. So the first term here, when n is 0, I get a 0. So I'm just going to remove that term and start at n equals 1 to infinity and c sub n x to the n minus 1. And then I'm going to re-index like we did in the last video. And this is going to become n equals 0 to infinity n plus 1 c n plus 1 x to the n. My goal here is to get series that are indexed starting at 0 and have the same degree x to the n where they start, so that they'll all be like terms starting at x to the 0, and I'll be able to add things together. Now there's going to be some problems with that when we move forward, when we start throwing extra x's in up here, but we'll get to those in a few problems. So n times n minus 1, cn x to the n minus 2. So 0 and 1 are both going to give us zeros. So we'll start at 2, and then we have n times n minus 1, cn x to the n minus 2. And that's going to become n equals 0 to infinity, n infinity, n plus 2, n plus 1, cn plus 2, x to the n. All right, so let's go ahead and write that the last way that we had it. N plus 2, n plus 1, cn plus 2, x to the n, plus n equals 0 to infinity, cn xn equals 0. So these are alike. I'm going to combine the series together, make it n plus 2, n plus 1, cn plus 2 plus cn, x to the n factors out. Now I don't want x to the n to be equal to 0 because that solution is just x equals 0, and that's kind of silly. We know that the series is going to converge at its center. I'm not interested in that. I'm interested in everywhere else where it's going to converge here to 0. So I want to take this part and set it equal to 0. And I'm going to solve for the higher indexed coefficient here. Like so. And then we're going to divide. And you'll notice that our starting with natural numbers, or sorry, whole numbers here. So our n started at 0 for our series here. So that's the first n that we're going to be able to plug in here. So the first c that we can get out is c2, meaning that c0 cannot be defined by this formula. C1 can also not be defined by that formula. C2 can, and it'll be in terms of C0. So when n equals 0, we have 2 times 1 is 2. That's a -1/2 C0. C3 is when n equals 1 is going to be 3 times 2 is 6, so -1/6 C1. C4 is going to be when n equals 2. 4 times 3 is 12. That's -1/12 C2, but C2 is already defined as -1/2 C0. So that's 1/24 C0. I don't know if you see the pattern of the factorials on the bottom here, but this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. The next one is going to be 5 factorial. So we're going to have a positive here as well, but this is going to be, let's see, negative, and then that's going to be 5 times 4 is 20. C3, -1/20 times -1/6. C0, sorry, C1 is 1/120 C1. That's enough for me to figure out what's going on here. So the C0s are all of the even powers and the even factorials here. So C0 by 1 is C0 times 1 minus 1/2 x squared plus 1/24 x to the 4th. The next one will be negative. And y2 is going to be my C1s, is going to be x minus 1/6 x cubed plus 1/120 x to the 5th. And the next one will be negative. And so this is, let me write the series form of these because it can be simplified a little bit. N equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. And I'll tell you in just a second what this is, if you don't remember that from Calculus 2. And this is going to be -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Again, I'll tell you in just a second what that is. Let's go back and let's solve this using our techniques from chapter 4. So y double prime plus y equals 0, m squared plus 1 equals 0, m squared equals a -1, m is equal to plus or minus I. So that gives us a y equals c1 cosine of x plus c2 sine of x. And so this is c0 cosine of x, that this is the even function here, all the even powers. And this is c1 times sine of x. This is the Maclaurin series here for sine of x. So my power series solution agrees with what I got from my method in chapter 4 with case 1, case 2, and case 3 for homogeneous linear differential equations with constant coefficients. Let's go ahead and also look at number 5, which we're going to do both ways again. And this will be the last one that we do both ways. This is just to establish that this technique is actually working and giving us the right answer. So y double prime minus y prime equals 0. Y is going to be equal to series n equals 0 to infinity, cn x to the n. Y prime is n equals 0 to infinity, and cn x to the n minus 1. And we know that we can get rid of that first term. Really wish it wouldn't do that. I'll just leave it this time. It's not going to cooperate. And y double prime equal to n equals 0 to infinity, n times n minus 1, cn x to the n minus 2, to n equals 2 to infinity, n times n minus 1, cn x to the n minus 2 is equal to n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, x to the n. So n equals 0 to infinity of n plus 2, n plus 1, cn plus 2, x to the n minus n equals 0 to infinity, n plus 1, cn plus 1, x to the n equals 0. Combine these together, n equals 0 to infinity of n plus 2, n plus 1, cn plus 2, minus n plus 1, cn plus 1, x to the n equals 0. We don't want the x to the n part to be equal to 0, so we want to set n plus 2, n plus 1, cn plus 2, minus n plus 1, cn plus 1 equal to 0. Solve for cn plus 2. It's 2, n plus 1, cn plus 2 equals n plus 1, cn plus 1. N plus 1 is going to divide out. Cn plus 2 equals 1 over n plus 2, cn plus 1. C0 is going to be not defined by this, neither is C1. We're going to be starting with C2. So we have C2 is equal to, when n equals 0, 1/2 of C1. C3 is going to be 1/3 of C2, which is 1/6 of C1. C4 is 1/4 of C3, which is 1 over 24 C1. C5 is 1/5 of C4, which is 1 over 120 C1. So we get y1 equals C0. Y2 is equal to C1 times x plus 1 over 2x squared. So 1 over 6x cubed plus 1 over 24x to the 4th plus 1 over 120x to the 5th plus ... is going to be equal to C1 summation n equals to 1 from 1 to infinity of x to the n over n factorial. Now, recall that if I had summation n equals 0 to infinity of x to the n over n factorial, that would be equal to e to the x. And I only vary by a constant here, which would get absorbed into this constant, because if I added n equals 0 in here, I'm going to get 1 over 1. So I can subtract that out. Let me show you what I mean, that my y total right now is C0 plus C1 n equals 1 to infinity x to the n over n factorial. If I change this index here to be n equals 0 to infinity to add another term in here, then I've just added 1 to the series, so I subtract 1 to balance it out. And so that's going to be C0 minus 1 is still a generic constant. So this is still some constant plus that I'll call C0, even though it's different than that one, C1 e to the x. So maybe I'll call it C2, just to be fair, because it's a slightly different constant, right? But it's a constant plus a constant times e to the x. Let's go ahead and look at what would happen now if we had y double prime plus y prime equals 0 and used our method from chapter 4. And we factored. This is minus, apologies. This is minus. So this is m equals 0, or m minus 1 equals 0, m equals 1. So y equals C1 e to the 0. It's just C1 plus C2 e to the 1x is x, like that. And you can see that they're the same answer. I had to do a little bit of work here to make them look identical, but that constant just goes over into the C0 part, and the C1 part has all of the e to the x terms in it. So, all right, there we go. And now we're ready to look at some things that we couldn't have done from chapter 4. So those first two problems, even though they could have been done old ways, we were showing that the new method worked. Now let's show you something that we have to use the new method for. That's going to be y double prime plus x y equals 0. So I've never done this before, where we just threw in an x as a multiplier. We've done constant coefficients. We haven't done variable coefficients other than when we did Cauchy-Euler, where everything had to have a multiplier that matched the order of the derivative, and we don't have that right now. So nothing I can do to fix that either. If I tried to multiply through by x squared to get this one to match, that one's not going to match. So this is not Cauchy-Euler. So we can't use any of our old techniques. Let's just use our new technique, n equals 0 to infinity, cn x to the n, y prime equals n equals 0 to infinity of n cn x to the n minus 1 is equal to, and you don't have to do this every time. I'm just showing you all the steps every time in case someone fast forwards to another one of the examples without seeing everything that I did. At first, I want everybody to see all the steps every time. but you could maybe write this down for yourself on a little sheet, especially if you're going to have something that's open notes and you can see y is always equal to this, y prime is always equal to this, y double prime is always equal to that. You might even want to go all the way out to y triple prime to see what it is if you think that your teacher might give you something that is going to have up to a third derivative in it. There are some examples in the textbook that have those. I'm not doing any of those today. Just I want to give you some examples, but I'm not going to do everything that's in the textbook for you. So that's an n minus 2. And then this is n plus 2, n plus 1, cn plus 2, xn. You see that each time that you have more to multiply by, it's harder to write it all on the line there. That's kind of why I'm sticking to things that only have up to the second derivative in them. So n equals 0 to infinity of n plus 2, n plus 1, cn plus 2, x to the n, plus x times n equals 0 to infinity. I'm going to show you something that I'm going to do here. I'm going to write it one way first, and then I'm going to show you that that's probably not the smartest way to go about this. And we'll fix it. So if I do this first, what I'm going to have to do is multiply this in there and add 1 to that power. And now this starts at the first power and is indexed at 0, but this starts at the 0th power and is indexed at 0. So I'd have to pull a term off of this and get them to match, right? But I don't have to do that. I'm going to take advantage of the second form that I have written here and say, well, I can go back and write this as n equals 1 here. Sorry, this form right here. So n equals 0 to infinity, n cn x to the n minus 1. If I do that, now when I'm supposed to be writing y, not y prime. So no way for me to fix this. Next problem, when I multiply x times y prime, I'll use this one and it will go in there. I was thinking ahead to the next problem, but I'm kind of stuck. So no way to use one of my alternate forms to help me here. I have to go about this the long and hard way. So plus 2, n plus 1, cn plus 2, x to the n, plus n equals 0. I guess that's good for the first one, that you have to see all the steps here before I start thinking and not really shortcutting, but let me explain to you what the problem is now. So again, this one starts at x to the first power, this one starts at x to the 0 power, which is not good. So I'm going to stick in this first term x equals 0. 2 times 1 is 2, c sub 2, x to the 0 plus, and then this starts at n equals 1 to infinity, n plus 2, n plus 1, c sub n plus 2, x to the n, plus n equals 0 to infinity, cn x to the n plus 1 equals 0. Yes. So now what I'm going to do is bring this back down to 0 and bring everything up by 1 inside here. And I'll remind you again why that works. So let's look at where we had started here when n equals 1. This is 3 times 2 is 6. C sub 3, x to the first. So we're looking for a first term of 6, C3, x to the first, right? So now my first term is 3 times 2 is 6. C sub 3, x to the first. It's generating the same series. When I take the index down by 1 and add 1 to all of the n's on the inside, I'm forcing exactly the same series as what I had. Why did I do that? Why did I change the way that it looked? Because I wanted my series to start at the same place and my x's to have the same powers so that I can combine the series together into one series here. N equals 0 to infinity of n plus 3, n plus 2, c sub n plus 3, plus c sub n, pull out that x to the n plus 1, set all that equal to 0. Now, we haven't had this before, but I think it should make sense to you that the only way that this all equals 0 is if this part is 0 and this part is 0. So 2c2 needs to be equal to 0, and n plus 3 times n plus 2, c sub n plus 3 plus cn needs to be equal to 0 because we're not letting x be 0. That's silly because we centered it at 0. We know that it would be 0 there. That's not an interesting solution to us. So n plus 3 times n plus 2, c sub n plus 3 equals a negative cn. So c sub n plus 3 equals a negative 1 over n plus 3 times n plus 2, c sub n. All right. Let's go ahead now and find these coefficients here that we need. C0 equals C0, C1 equals C1. C2 has already been defined there as being 0. We can start using our equation here for C3, which is going to be when n is 0, 3 times 2 is 6, so negative 1/6. C0. C4 is going to be when n is 1, 4 times 3 is 12, so negative 1/12. C1. C5 is going to be based off of C2, so that's going to be times C2. That's also going to be 0. So every third step here is going to be 0. We just go ahead and write that out. 6, 7, and 8. That one's going to be 0. So that's going to be my 3 sets here that I'm going to use for defining my series here. I'm not going to go out any more than that. So when C is going to be 0, 1, 2, 3, 6 times 5 is 30. C what did I say this is? This is when I'm at C, n equals 0, n equals 1, n equals 2, n equals 3, right? So that's C3. This is n equals 4 and n equals 5. So negative 1 over 30, C3 is negative 1 over 6, C0. It's 1 over 180, C0. This is equal to when n is 4. That's negative 1 over 42. C4 is negative 1 over 42 times negative 1 over 12. C1, which is a big number. And it's one of the other reasons that I'm stopping there. 84, 42, 504. Negative, negative is a positive. C1, okay, that's enough for me. If you want to go a little further, you can, but you'll probably need the assistance of a calculator for that. So my y1 is going to be c0 times 1 plus a negative 1/6 x cubed plus 1 over 180 x to the 6th. Notice that we're going every 3 here. The next one will be negative dot dot dot. Y2 is going to be C1 times X. And then the next one's going to be when we get to X to the 4th, so minus 1/12 X to the 4th plus 1 over 5/4 X to the 8th. And then that's going to be minus again, dot, dot, dot. And there's really no reason to try to find a closed form for that. That's enough because you have the formula that generates more constants. If you need to go more, the idea here is if we can get far enough out here, we can get really good approximations because we're reducing the error as we add more terms. So going out to this 8th degree polynomial, I mean, that should be pretty good as long as we're staying really close to values of x equals 0 here. We should be doing really great using this this series to approximate the answers that we would get to our as our solutions. So the this is the exact answer. Obviously, you can't add an infinite amount of terms. So yeah, you can't do all the work for that. So, all right, let's go ahead and let's move on now to, that was number, I think that was number 7. Yes, and let's move on to number 9. Y double prime minus 2x y prime. You'll see what I was talking about here, that my x is times my y prime this time. And I'm going to be able to use a little technique to be able to help me. I'll go ahead and list out everything like I did before. Cn x to the n, y prime is n equals 0 to infinity of n c sub n x to the n minus 1. And I was tempted to leave that. It does it again. Okay, it didn't do it that time. And this is going to be equal to n equals 1 to infinity. Yeah, I'll just leave it. It's not going to cooperate. Thinks I'm trying to draw shapes. Its first impression is that when I draw a sideways figure 8, then I'm trying to draw an ellipse and don't know how to close my ellipse. So n plus 1, Cn plus 1, x to the n. So y double prime is equal to n equals 0 to infinity of n times n minus 1, c sub n x to the n minus 2 equal to n equals 2 to infinity of n minus 1 cn x to the n minus 2 is equal to n equals 0 to infinity. Oh, that's new. N plus 2, n plus 1, cn plus 2, x sub n. All right, so now I want to think smarter, not harder. So n equals 0 to infinity of n plus 2, n plus 1, cn plus 2, xn, minus, I'm going to bring the 2x in, but I'm going to do it on this form right here that already starts at 0. When I bring the x in, it's going to make this the nth power. So n equals 0 to infinity of 2 2n cn x to the n plus n equals 0 to infinity cn x to the n, and that all needs to be equal to 0. So now everything starts at 0 and ends with an x to the n. So I can combine everything into a single series here, making my life easier. N plus 2, n plus 1, c sub n plus 2, minus 2n c sub n, plus c sub n, x sub n on the outside equals 0. So this is n equals 0 to infinity. Whatever. You know what that's supposed to be. N plus 2, n plus 1, c sub n plus 2. And then this is plus a negative 2n plus 1 c sub n, or minus 2n minus 1 en x sub n equals 0. All right, now that I have all that, we didn't have to peel any terms off here. N plus 2, n plus 1, cn plus 2 minus 2n minus 1, c sub n is equal to 0, solving for cn plus 2, n plus 2, n plus 1, c sub n plus 2 equals 2n minus 1, c sub n. And dividing here, c sub n plus 2 equals 2n minus 1 over n plus 1 times n plus 2 c sub n. So we need C0 and C1 to be defined outside of this formula. C2 is going to be when n equals 0. This is negative 1 over 2 C0. C3 is going to be when n equals 1 is going to be 2 minus 1 is 1. 2 times 3 is 6. C1 when n equals 2. C4 is equal to 4 minus 1 is 3 over 3 times 4 is 12. C2, so that is 1/4 of negative 1/2 C0 is negative 1/8 C0 when n equals 3. Now, sometimes it's not to your benefit to reduce fractions. If you're going to be able to find a closed form, you're not going to be able to find a nice, easy closed form here. So I don't really care about reducing the fractions here. When n equals 3, this is 5 over 4 times 5 is 20. C3 is 1/4 times 1/6 C1. It's 1 over 24 C1. I think that's enough for me. I've got, let's see if I want any further. That's, I'll go a couple more terms here. When n equals 4, C6 is equal to 7 over 5 times 6 is 30. C4, 7 over 30 times negative 1 over 8. C0 is negative 7 over 240. So, right, so when n is 4, 8 minus 1 is 7, 5 times 6 is 30, 7 over 30 times negative 1 over 8 is negative 7 over 240 C0, right? And then when n equals 5, we have C7 is equal to 9 over 6 times 7 is 42. Both of those are divisible by 3. So that's 3 over 14. C5, 3 over 14. And then 5 is 1 over 24. C1, 3 goes into 24 8 times. And that is 1 over 32. So that's 112 C1. Okay, so this is going to be something like y equals y1 equals C0 times 1 minus 1/2 x squared minus 1/8 x to the 4th minus 7 over 240 x to the 6th minus dot dot dot. You see the C0 terms are negative here, the C1 terms are positive. Y2 equals C1 times x plus 1/6 x cubed plus 1 over 24 C1 x to the 5th plus 1 over 112 x to the 7th plus dot dot dot. So the book came up with a more closed form that I wouldn't have expected you to find, where it was not reducing the fractions, and it came up with a way to write it with factorials in the bottom. And so you can look at that answer and see that it matches the answer that we got. Hopefully, I didn't make any arithmetic mistakes, but let's go ahead and let's do another example here. And we have y double, this is number 11. Y double prime plus x squared y prime plus xy is equal to 0. So we got lots and lots of things going on here. You know that your y equals n equals 0 to infinity, Cn xn. Your y prime is equal to n equals 0 to infinity, n Cn xn minus 1. Just going to leave them this way for a second. Y double prime equals n equals 0 to infinity, n times n minus 1, Cn x to the n minus 2. The reason I want to leave them looking that way for a second is that I think that I'm going to be able to get a couple of these to match the degree just by the multipliers. Can't really do anything about this one, so I'm gonna make it start like I normally would at n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, xn. But these other two, when I multiply x squared in here with this form, I get n equals 0 to infinity, n cn x to the n plus 1, plus, and then when I multiply x into this one, I get n equals 0 to infinity, cn x to the n plus 1. That needs to equal 0. So I've got two of them that start at 0 and x to the n plus 1. This one starts at x to the n. So I need to get rid of this 0th term here. 2 times 1 is 2. C2 x to the 0. So this is going to be plus n equals 1 to infinity. N plus 2, n plus 1, cn plus 2, xn, plus I already put these together, n equals 0 to infinity, n cn plus another cn is going to be n plus 1 cn x to the n plus 1 equals 0. And then I'm going to fix this one, n equals 0 to infinity, n plus 3, n plus 2, cn plus 3 plus n plus 1 cn x to the n plus 1 equals 0. So 2c2 equals 0. C2 is equal to 0. And n plus 3, n plus 2, c sub n plus 3 plus n plus 1, c sub n is equal to 0. Solving for cn plus 3. Then we get c sub n plus 3 equals to negative n plus 1 over n plus 2 times n plus 3, c sub n. All right, let's take a look at what those coefficients come out to be. So C0 is going to be C0, C1 is going to be C1, C2 is 0, C3 is going to be when n equals 0, is going to be negative 1 over 6, C0, when n equals 1. C4 is going to be negative 2 over 3 times 4 is 12, C1, so that's negative 1/6 C1. When n equals to 2, it's going to be C5 is going to be equal to 0. Let's see, 6, 7, 8 is 0. So n equals 3, 4, and 5. I'll probably stop with them. So n is 3. This is negative 4 over 5 times 6 is 30. And negative 2 over 15. C3. So negative 2 over 15 times negative 1/6 C0. 1, 3. So 1 over 45 C0. Myself a little bit more space here. N equals 4 is C7 is equal to negative 5 over 6 times 7 is 42. C4, negative 5 over 42 times negative 1/6. C1 is 5 over, this is 252. C1. And then, as I said before, when n equals 5, C8 is going to be 0 again. That's enough for me to start to write my equations here. So y1 equals C0 times 1 minus 1/6 x cubed plus 1 over 45 x to the 6th. The next one will be negative because it's changing signs, positive, negative, positive, negative. Y2 is C1 x, and then minus 1/6 x to the 4th plus 5 over 252 x to the 7th. And then this is going to be minus, again, because going plus, minus, like so. And again, I believe the book has a more closed form for that involves squares and factorials and things, but we'll go ahead and leave it there. I believe the teacher would be pretty happy with that if you could get that. Moving on to number 13. X minus 1 y double prime plus y prime is equal to 0. So I'm going to write that as x y double prime minus y double prime plus y prime is equal to 0. And so x y double prime is equal to x times n equals 0 to infinity of n times n minus 1 c n x to the n minus 2. So that's going to be n equals 0 to infinity n minus 1 cn x to the n minus 1. We'll work on that in a minute to see what we need to bring that up to. Y double prime is equal to n equals 2 to infinity of n times n minus 1 cn x to the n minus 2, and I can bring that up. So this one here, I'm going to eliminate that first one, make that start at 1 so that it starts at x of 0. This is going to start at x of 0 when I fix it. And let's see, y prime is going to be n equals 0. Let's say 1 to infinity n times cn x to the n minus 1. All right, so I've got everything written in such a way so that when I change the indices, that these are all going to start at 0 and they're all going to go up to x to the n. So my first one here is going to be n equals 0 to infinity, n plus 1 times n, cn plus 1, xn, then it's minus n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, xn, plus n equals 0 to infinity, n plus 1, cn plus 1. All of this is going to be with a big old x to the n on the outside. Equals 0, like that. So let's go ahead and try and write this all as a single series here. So let's see, we have n squared plus n plus n plus 1, cn plus 1 minus n plus 2, n plus 1, cn plus 2, xn equals 0. So all that comes from this and this are both cn plus 1 terms that can combine here. This is n equals 0 to infinity, n squared plus 2n plus 1, c sub n plus 1 minus n plus 2, n plus 1, cn plus 2, xn equals 0. Let's just drop the summation here. So this is n plus 1 squared, c sub n plus 1 minus n plus 2 times n plus 1, c sub n plus 2 equals 0. We'll be able to divide out by an n plus 1, so n plus 1, cn plus 1 minus n plus 2, cn plus 2 equals 0. Going to solve for the one with the higher index, which is the cn plus 2, so negative n plus 2, cn plus 2 equals a negative n plus 1, cn plus 1. Negative divided by a negative is a positive. C sub n plus 2 equals n plus 1 over n plus 2, cn plus 1. All right. So that gives me C0 equals C0, C1 equals C1, then C2 is going to be when n equals 0 is 1/2 C1, n equals 1. C3 is 2/3 C2, which is 1/3 C1. Then when n equals 2, C4 is 3/4 C3, which is 1/4 C1, and so forth. If you want to see another one, when n equals 3, C5 is 4/5 C4, which is equal to 1/5 C1. So we have Y1 is equal to just C0, and Y2 is equal to C1 times x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th plus 1/5 x to the 5th plus ... So that does look like something that we could have answered before, that has a form that appears to be related to e to the x here. And so anyways, that is fine for our series solution. But like I said, we could have added 1 here and then subtracted 1, and that would have gone in with that constant there, and we would have ended up with a solution that would have looked like a constant plus a constant times e to the x. This is very similar to our previous problem that we did, so where I already mentioned that. Let's go ahead and look at number 15. Y double prime minus x plus 1 y prime minus y equals 0. So this is going to be y equals n equals 0 to infinity c sub n x to the n, y prime equals n equals 0 to infinity of n cn x to the n minus 1, which is n equals 0 to infinity of n plus 1 cn plus 1 x to the n. Y double prime is equal to n equals 0 to infinity of n times n minus 1 cn x to the n minus 2, which is equal to n equals 0 to infinity n plus 2 n plus 1 cn plus 2 xn. So let's look and see which pieces here are going to match up for me to all start at 0 and go to x to the n. So this is going to be y double prime is n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, x to the n. And then if I had x times y prime, so let's come back to this form here, n equals 0 to infinity, n cn x to the n. and then plus y prime. So I'm going to add this form over here, n equals 0 to infinity, n plus 1, cn plus 1, xn minus regular old y, n equals 0 to infinity, cn xn. That all needs to equal to 0. So we have big summation n equals 0 to infinity of n plus 2, n plus 1, cn plus 2 minus n cn plus n plus 1 cn plus 1 minus cn x to the n equals 0. It's going to be n equals 0 to infinity, and then there's only one cn plus 2 term. So let's write that here. It's only one cn plus 1 term. And then minus n plus 1 cn, because it's a negative n and a negative 1 here. So I see n plus 1s in everything. That'll be helpful in just a second. So we're going to have n plus 2, n plus 1, cn plus 2 plus n plus 1, cn plus 1 minus n plus 1 cn equals 0. Divide all these parts out. N plus 2 cn plus 2 is equal to a negative 1 cn plus 1 plus cn. And cn plus 2 equals a negative 1 over n plus 2 cn plus 1 minus cn. Just factor the negative 1 out of this and put it as the fractional coefficient there. I think that probably looks and works better. So we need C0 and C1 defined outside of this equation when n equals 0. C2 is going to be negative 1/2 of C1 minus C0. Just going to check my signs on everything here because something doesn't match with what I have here. So plus, minus, plus, minus. Let's just check up here to make sure that that's right. This should be minus, minus. That's what's wrong. So this is minus was on the outside. So that's minus. That's minus. That is minus. And that is minus. So that makes this plus and plus, plus. All right. So that's correct. All right, so now we have positive 1/2, and then C1 plus C0. That works for me. C3 is equal to, that's when n equals 1. C2, 1/3 of C2 plus C1 is going to be 1/3 of C2 is 1/2 of C1 plus C0 plus C1 is going to be equal to 1/6 of C1 plus C0 plus another C1 is going to be equal to uh, 3 is 1/3 of C2 plus C1 is 1/2 and 1/2. Yes. So that is 1/3 of 1/2 of C1 plus 1/2 C0 plus C1 is 1/3 of 3/2 of C1 plus 1/2 of C0 is equal to 1/2 of C1 plus 1/6 of C0. You're going to see very quickly that I'm getting 2 terms for each one, so I'm going to not do nearly as many n's here. So C4 is going to be my last one that I'm going to do here. It's going to be 1/4 of, and then this is going to be C3 plus C2, which is 1/4 of C3 is 1/2 C1 plus 1/6 C0. C2 is 1/2 of C1 plus C0. So that's going to be 1/4 of, and then 1/2 and 1/2 is a whole, and 1/6 and 3/6 is 4/6, which is 2/3. So that is 1/4 C1 plus 2 goes into 4 2 times. So this should be 1/6 C0. All right. And let's go ahead and write my equations here. Y equals C0 times 1 plus, and then there's a 1/2 C0 that's in my x squared term, and there is a 1/6 C0 that's in my x cubed term, and there is a 1/6 x to the 4 C0 in my x to the 4th term plus dot dot dot, and y2 is equal to C1 times x plus, and there is a 1/2 C1 in my x squared term plus a 1/2 C1 in my x cubed term plus a 1/4 C1 in my x to the 4th term plus dot dot dot. Then I want to do one more. I know this video is going kind of long, but I really think that it would be helpful to get all these examples out of the way in one video for you. So we're going to do one more here, and that's going to be x squared plus 2 y double prime plus 3x y prime minus y equals 0. We have y equals n equals 0 to infinity, c sub n x to the n. Y prime is equal to n equals 0 to infinity, and c sub n x to the n minus 1, and 3x y prime is going to be then n equals 0 to infinity of 3n c n x to the n. Y double prime is going to be n equals 0 to infinity of n times n minus 1 cn x to the n minus 2. So 2, which is equal to n equals 0 to infinity, n plus 2, n plus 1, cn plus 2 x to the n. So 2y double prime, I'm going to use this form over here, is going to be n equals 0 to infinity, 2 times n plus 2, n plus 1, cn plus 2, x to the n. And when I have x squared y double prime, I'm going to use this first form. That's going to be n equals 0 to infinity, n times n minus 1, cn x to the n. All right, so let's add our pieces parts together here. So I have x squared y double prime plus 2y double prime plus 3xy prime minus y needs to be equal to 0. So that's going to be this one, equals 0 to infinity. I have n times n minus 1 cn, then plus 2y prime, so I have plus 2 n plus 2 n plus 1 cn plus 2 plus 3 y prime, so that's going to be plus 3n cn, and then we have minus cn x to the n equals 0. So let's look at the pieces that we have that are alike. Equals 0 to infinity. We have cn. We have cn plus 2. We have cn and we have cn. So let's try and get all those cn's together. N squared minus n plus 3n minus 1 cn plus 2 times n plus 2 times n plus 1 cn plus 2 x to the n equals 0. Going to be n equals 0 to infinity n squared plus 2n minus 1 cn plus 2n plus 2 times n plus 1 cn plus 2 x to the n equals 0. Drop the x to the n part out, and we get n squared plus 2n minus 1 cn plus 2 times n plus 2 times n plus 1 cn plus 2 equals 0. Solving for Cn plus 2, we get 2 times n plus 2 times n plus 1 times Cn plus 2 equals negative quantity n squared plus 2n plus 1 Cn. And that means that C of n plus 2 is equal to a negative n squared plus 2n plus 1 over 2 times n plus 2 times n plus 1 Cn. Let's go ahead and let's generate some coefficients here. So we know C0 equals C0, C1 equals C1, C2 is when n equals 0 is going to be, and I've already figured these out so that I can write them out a little faster for you here. So this is going to be C0 over 4, C3 is going to be negative 2C1 over 12, which is going to be negative 1/6 C1. C4 is going to be equal to a negative 7 C2 over 24, which is a negative 7 over 24 C0 over 4 is a negative 7 over 96 C0. C5 is equal to a negative 9 plus 6 minus 1 C3 over 2 times 5 times 4 is equal to a negative 14 C3 over 40 is a negative 7 over 20. C3 is a negative 7 over 20 times negative 1/6 C1, which makes this a 7 over 120 C1. And that gives me Y1 equals C0 times 1 plus 1/4 x squared minus 7 over 96 x to the 4th plus dot dot dot. And Y2 is equal to C1 times x minus 1/6 x to the 3rd plus 7 over 120 x to the 6th minus dot dot dot, because these are alternating in sign. After the first term here, plus minus plus minus, this is minus plus minus plus, so on. So there you have it. That's all the examples that I wanted to do for you in this video. Hope that was really helpful. Next time we're going to come back and we're going to do solutions about a singular point with the method of Frobenius. And that's going to be far fewer examples because each example is much longer. So probably only a couple problems in that video. So hopefully it will be enough to let you whistle a little bit, but to show you that we would much rather find a solution around an ordinary point than around a singular point. But the method is there in case you absolutely have to find a solution centered around a singular point. All right, see you for the next video.